I'm going to discuss embeddings, and of course, embedding is smooth, and of course, manifolds. And so I'm going to discuss two things. So let me just one, we are going to discuss embedding of three manifolds in 5 manifolds, where n could be something like 5 or 3. And these embeddings we'll discuss in smooth and smooth category and contact category. And what I mean in this category, there are two further kind of question that one can study. One is this called contact embeddings. Where we just put a contact structure on the target manifold. And we ask the question whether you can find an embedding whether the pullback of alpha n is the contact structure on it. So you just start with some m and you embed in such a way that embedding induces the context structure on. On the other hand, you can ask slightly more kind of stronger question is that you start with. So start with m and a context structure on m. And the question is, so is there a embedding n such that star of alpha n is g times percent g positive available. Okay, so this says that you can embed in such a way that you restrict the context structure to this f of m, then it actually induces a context structure. While in the second case, it says that I've been given a context structure and I have to, in addition, ensure that it's not just a context structure, but it's a given context structure. Okay. Now, and similarly, I discuss here embeddings of 4 manifold in 6-dimensional manifold. And again, this we will discuss in just the case of smooth embeddings and symplectic. And just as in the case of contact case, you can again ask two questions that if I have a symplectic structure, can I find an embedding such that that embedding is symplectic? That means the symplectic structure induces a symplectic structure on this. Or you can also ask that if I start with a symplectic manifold, is it possible to embed in such a way that embedding is not only symplectic, but it induces a given symplectic structure? So these both question you can discuss.
In both cases, you're free to choose the symplectic or contact structure on the target.
Yeah, target, whether there is such a, I mean, which manifold you take, you, yeah, choose meaning, not like for every X, you can, if you choose a Y, it has no meaning, correct? Because of course, X embeds in X cross some manifold. So you can think of that this manifold is something fixed, like CP1 cross CP1 cross CP1 or CP3, some standard symplectic manifold, which is somewhat simple.
Right, but the symplectic structure on Y can be changed.
No, I generally, when I talk of the second question, I fix the symplectic structure on Y and try to see whether all of them go inside. Yeah. So let me kind of very quickly say that why I am kind of first interested in the case of codimension two manifolds, embeddings in codimension 2. And the reason is that if the codimension is higher, then these embeddings kind of abide by H principle, at least at the pi naught level, meaning if you can find a formal embedding, then you can produce a appropriate embedding. So codimension for a closed manifold, there's for open manifold, even in this dimension, it's okay. So we will mostly focus on closed manifold or an embedding which is proper, in the sense that if you talk of manifold with boundary, then boundary should go to boundary.
Maybe also for kind of people who not in the area, worthwhile to know the following. So this either symplectic or either contact problem, it on the surface it looks like isometric embedding. So it's also like satisfying some huge system over determined system of differential equation. But in reality, it is not, because it's if you induce symplectic structure, for instance, or contact structure, which is a homotopic to original via kind of contact homotopy, then you can correct your embedding by just reparametrizing the manifold by this kind of Mozart type argument. So okay.
Is it important here that we are talking about embeddings rather than just immersions that we don't have self-aware?
Yeah. And so also I must tell that this contact embedding, even in codimension 2, actually follows that H principle, that if you have a formal contact embedding, then you actually have contact embedding. But at least as far as my understanding and trying to understand this embedding is concerned, it's always extremely difficult if you just go to literature and look at the already existing various embeddings that they have constructed and then try to say whether you can actually get a formal embedding out of it. Simply because, when you just produce smooth embedding, you don't keep track of this geometric structure of contact or symplectic. Reason we wanted to understand this smooth embedding is also because we wanted to make the smooth embedding in some sense compatible with this geometric structure. So I'll come to it. So let me first kind of make and I'm also studying both this case simultaneously, because I will hopefully be able to demonstrate that just with one idea you can deal with both this case, because in some sense you can regard contact 3 manifold as boundaries of symplectic 4 manifold, and so you can kind of produce this embedding in such a way that essentially you can produce embedding symplectic manifold in such a way that it also gives embedding of contact manifolds. I mean, it's not, I'm cheating, it's not exactly true, but I will show you that the techniques are similar in proving this kind of. So, but let me just give some few kind of sample of the kind. Let me give you some idea of what kind of results we have obtained. And so here is some. First is, so S5, and this is with, of course, we kind of reprove a classical result which was proved by many people.
What is the people you wrote?
This is my students. Yes, I.
But it's not the people who originally proved this.
No, I am writing now. This is. Here's, I mean, there are many people here. I'm not giving full extensive, but like this is proved in with different methods several times. So this and second result is, so M I M. Okay, so this. So this, whenever you can kind of produce an embedding such that pullback induces the given embedding, this embedding is called as isocontact embedding. So you are starting with a contact structure on a manifold, and you want to embed in such a way that pullback from this bigger manifold produces the given contact structure. This is called isocontact embedding. That is what probably Asha was mentioning, that it's like isometric. You want the same geometric structure. So the second result is that this M3 with a contact structure, isocontact embeds in S5 only if the first M class of this contact structure is 0. And this, okay, this actually has been kind of proven in two different ways. For first one is with Suhas Pandit, and the next one is with transgressors. And in fact, we have kind of extended this to give a even in higher dimension embedding result, and in fact, proved an sort of pi naught surjection. That means if you have a formal isocontact embedding, then you get an actual isocontact embedding. But let's just focus on the low dimension case. And now, let me say, hello. So let me set now results about 4-dimensional manifolds inside 6-dimensional manifold. And the first is that any X4, by I mean closed orientable. So this embeds inside this is with my Abhijit convert. And so this, or you can in fact change this target manifold to some more manifold like CP3, CP2 cross CP1. And I think that this is kind of codimension, finding a 6 manifold where all 4 manifold orientable embeds is probably was not known. What was known in general was, I mean, what was known about smooth embedding is that if you take X4, then X4 embeds in S6 if and only if I think W2 X4 is 0. Okay, so this was the best known result. When we have, of course, in general, we have shown that if you replace this S6 by CP3, then all of them.
What does W2 X4 denounce?
Huh? Second Stephen.
Okay.
Second Stephen.
Is that embedding to CP1 crossing? Is that symplectic?
I'm coming to it. Now I'm on smooth category.
Okay.
Actually, the embeddings are produced in such a way that smooth category it just comes as a corollary in some philosophical sense. And in symplectic category is the following. That let's be a symplectic manifold. Which admits lattice vibration. Then there exists symplectic embedding. Exploring where there's a symplectic form on CP1 cross CP1 cross is just you just take the volume forms on each of, fix on CP1 and look at the projection and pull back the form and add them. So that is the standard symplectic form.
But you can vary area and still embed. You don't care.
No, because I am just looking at a symplectic embedding, I will not bother about area because it will just produce some symplectic form here. If I want then isosymplectic embedding, then you have to play with area. But currently, I'm not saying anything about isosymplectic embedding.
But it's still not clear if you change this area, maybe even symplectic embedding does not exist.
In the way in which proof goes, the symplectic embedding should exist. Yeah, it's not clear, but
so to clarify, that says you're realizing as a symplectic submanifold of this.
no, but there is a condition here that it has a left-shift vibration. So what this condition means, let me just tell you that you start with a symplectic manifold. And after certain blow-ups, you get embedding. So currently, we can't say that you start with a symplectic manifold and that manifold embeds. That manifold, after making some connected some with CP2 bar, that admits an embed.
So that may be kind of for those who not expert again, it says that. So it's a theorem of Donaldson which says that every symplectic manifold admits a left-shift cancel. So which means not necessarily left-shift vibration, but kind of after blow up, it admits this one. And the conditions that this vibration exists, not going to blow up, but just on the spot.
Yeah. So when we do the proof, I'll probably kind of clarify Yasha's comment a little more. But currently, you can take it as that you cannot probably embed X4 itself, but you have to make connected with some standard object, which is the complex projective space with the reverse orientation, and then it embeds. Okay. And this is made because, as Yasha said, that there is some kind of pencil structure on this X4, and by making this connector, you can make it into satisfying the hypothesis that I have written in result 2. And so then there is an embedding.
Are there some known obstructions to having a left-shift vibration without blowing up?
Are there some?
Yeah, what's an example of the
In algebraic, for algebraic or symplectic?
or symplectic?
Yeah, but first of all, you need that, you need a CP1 with -1. I mean, so there are luscious vibration with, oh, you are saying the other way.
Yeah, that it doesn't emit a Lefschetz vibration, only Lefschetz pencil.
Any example when Lefschetz pencil does not, Lefschetz vibration does not exist.
Yeah.
CP2, how do you get vibration of CP2? You have to make all the CP1 intersect.
Like us.
I mean, you just compute the topology because it can have, it has no singularity. You can eliminate all the examples. In fact, you can write down all the genus 0 Lefschetz vibration.
Right, but you didn't say genus 0, right? It could be
No,
any.
I'm saying that in CP1, CP2 case, you can like just by topology, you can eliminate because you have given Lefschetz vibration means you can just calculate this topology starting with a disk cross a surface and adding 2 handles to it.
I see.
And that it will just not possible to get CP2 out of it.
Okay, because simply because the fiber has to have a self-intersection 0.
Yeah.
So it has to be trivial cost.
I see. I see. But then, so maybe with a little more work, you can also get some bound on how many blowups you need to do in general or something.
Or maybe you can just, everything goes, who knows?
Okay.
Everything with a little bit more work, everything is possible.
No, I am not saying like that.
Okay.
He's joking. I'm just saying that I have no clue. I would say that there should.
I was just wondering, so like,
So currently, I have a strong feeling that if you start with an algebraic manifold, then probably there is a bound.
but okay, so one more question. So is there an example where you need like arbitrarily many blowups, maybe just for topology reasons?
What do you mean by arbitrary manifold?
Like,
Meaning there are examples where
you have to blow up 100 times before you hit a Lefschetz.
yeah, because I mean you can construct a pencil with a base locus consisting of 100 points, then you have to blow
Right.
it up.
That one you have to blow up, but then there could be some other pencil on the same manifold, which.
Yeah.
Okay.
It could be possible, yeah. So I'm saying that this question is sort of somewhat easier to understand when you don't take arbitrary symplectic manifold, but you restrict yourself to the class of symplectic coming from the algebraic geometry.
But this condition about existence of Lefschetz operation, you don't know if it's necessary. It's efficient, but maybe it's not necessary.
It is not necessary. However, it is not necessary. However, the proof is constructed via reverse engineering, that if there was a symplectic submanifold inside another symplectic, then you would be able to produce a divisor that intersect the submanifold correctly, and so that pencil induces the pencil.
So which
So that was the original motivation to come up with this proof.
okay, I'll go there.
So there is a result by Danielu that you can, if you have a symplectic submanifold inside a symplectic manifold, then you can construct a Donaldson divisor that intersect the submanifold also into a divisor. And so the pencil here coming out of the divisor induces pencil there. So it's like pencil goes inside pencil. So we kind of did it from the other direction, that you just start with the pencil and put fiber into fiber. But it's of course not necessary. Can I continue?
CP2, for instance, can be embedded in CP3.
Yeah, but in a way that CP3's pencil induces pencil here.
Okay.
I mean, generic pencil of CP3 induces pencil there. Okay, I'll make comment later because of course you can.
You should go with your talk because you don't have much.
Yeah, sure. Okay, so I want to give a brief idea of what is the main technique in proving this kind of result. And the main technique is that this some geometric decomposition. So there are geometric decomposition of manifold which are kind of compatible with context structures in the odd dimensional case and symplectic structure in the even dimensional case. And so let me just write for this the geometric structure for M3 inside N5. And the structure is this open book. And so given I just take three manifold odd, an open book decomposition is a map where B is a manifold. And near B, this open book decomposition, this fibration is a very standard neighborhood. That means it just looks.
Not just map, but vibration.
Yeah. Thank you. The fiber bundle over is a fibration. And near B, so near B, the map looks like, the vibration looks like B cross 2 minus B cross 0 and just 6 x theta 2 theta. So it's just you take B and take B cross D2 and it just kind of move like the pages of open book. So it's like, yeah, I can just go into this is your B and it kind of locally just goes around it. Each fiber has common boundary, namely your B. So the vibration is defined in the complement. And so the thing that one should so now given a contact manifold, there is an associated open book decomposition. That means it's called a contact form is carried by an open book. I'm not going to define that precisely because I don't have time. But these are extremely important in studying context structure. And what happens is that given a contact manifold, essentially there is an open book decomposition such that the D alpha gives M minus B a structure of symplectic fiber bundle. So, and in case of symplectic manifold, you have this geometric decomposition called Lefschetz fibration, which is a map from, so let's just write here 4 dimensions. 4 CP1, the map with points, and such that locally near points, the map is given by, let's call it pi. So pi of is given by the following formula. So in this case also, if you check that if you kind of remove the inverse image of all the things that is mapped to pi p, then in the complement it is a fiber bundle. So in this case, locally,
Sorry, could you quickly review the difference between a Lefschetz vibration and Lefschetz pencil?
Lefschetz pencil is vibration. Lefschetz vibration is defined for whole X4. A pencil is defined in the complement of codimension for submanifold, where it is not defined and where it just looks like the map Z1, Z2 going to Z1 divided by Z2.
Okay, thank you.
So this fiber can intersect with some wall.
So let me continue here. So, yeah, and so if we, so in the complement of we have that this X4 is fiber bundle. With is disk with just. So in this case, there we produce in the complement of codimension 2 submanifold a fiber bundle over S1. In this case, you get a fiber bundle not over S1 but over a disk from which I have removed finitely many points. So there is a map. So let's call it U. Then there is a map from X4 minus that suitable set, some fiber, a surface. Base is now you see that in both the case, this fiber bundle is essentially determined by what happens when we kind of go around these points. Okay, so essentially topologically, you can think that this is a fiber bundle over wedge of circles. And this one, that one is just a fiber bundle over a circle. And so we would like to kind of understand how to put this kind of fiber bundle over circle in a nice way inside another manifold. And then hope that we put in such a way that we can extend the embedding to get an actual embedding of manifold. Yes, that's the idea. So let me now go to that part, how to produce the embedding. So I would like to make quick couple of remarks that since everything is kind of mostly so essential is to understand the fiber bundle over S1 with a fiber a surface, this this bundle is captured by what is called as monodromy, which is an element of the mapping class group of the surface. Okay, so it basically over S1, this fiber bundle is nothing but a mapping torus where phi is some diffeomorphism, and you identify, you take in case of 3 manifold, you take some sigma cross I and then identify sigma cross 0 with sigma cross 1 via some diffeomorphism, and this diffeomorphism up to isotopy determines the manifold that we get. Okay, so we are going to kind of keep this in mind when I try to discuss the proof. So, fiber bundles over F1 with fibers. Mine. Element of mapping class group. Yes. Corresponds to the monodromy. What is this monodromy? Because you have a fiber bundle over circle. For now, just take this as 3 manifold. You have fiber bundle over circle, so I can just take d by d theta and kind of look at its lift, and I start at some particular theta equal to 0 and look at the lift of the vector field d by d theta and go around and come back to the same page. And this gives a diffeomorphism between the page at theta equal to 0 and page at theta. So it's a self diffeomorphism of the page at theta equal to 0. That is my monodromy. I just lift the vector field to the whole manifold so that it is always transversal to the fiber, and at time 1 it comes back to the given fiber. Again, this is possible because you can just lift d by d. So, and once you get this diffeomorphism, you can check that if there is another diffeomorphism which is isotopic to it, then topologically there is no change, and both the manifolds are same. There is a diffeomorphism between them. So you just have to understand what are all these return map, up to isotopy. Okay. And so let us just take the simplest and let us just ask the simplest question, that you take the simplest surface, which is annulus. And you look at all possible fiber bundles over S1 with this annulus as a fiber. And you can check that they are determined by the mapping class group of this A, which is generated by diffeomorphism, which are known as bent twists. Okay, so you have A, and you have fiber bundle over S1, and so we asked the question: is it possible to kind of embed this inside, say, S1 cross B4 such that this embedding is fiber preserving. Okay, so this is a trivial fiber bundle as discussed before, and you project on the first factor. So this is a fiber bundle of dimension 5. And here you have arbitrary fiber bundle, but with the fiber annulus. So it is determined by some element of the mapping class group of annulus, which is a group of diffeomorphism which are identity on the boundary. And this group of diffeomorphism up to some diffeomorphism which is isotopic to identity. So you just, if two are isotopic to each other, then you call them same. You go mod the all, in the whole group of diffeomorphism, you go mod the one which are isotopic to identity. So this is mapping class group. And so you want to see, is it possible to embed the simplest kind of surface inside this in such a way that the fibers are preserved. And in order to kind of produce this embedding, you do what I call reverse engineering, in the sense, suppose it was possible to produce an embedding like this with this property, then you can, because this is trivial fiber bundle, you can project to the before and you would produce, so suppose F exists, then by projecting on before, we get a family FT of embeddings of annulus which satisfy the property that so that's a family FT of embeddings with F0 is equal to the given F. We satisfy the property that F0 followed by F inverse is 5 and the element of the mapping class group determined by this. That is bundle. So you just, so if you have a fiber preserving embedding, then you would have a family of embedding in before such that that element of the mapping class group actually appears via family of isotopies of before. Okay. And so we kind of ask that whether it is possible to achieve this. Is it possible to achieve this? That means, is it possible to find? So, is it possible to get embedding capital F of A in B4? So, let me just write this more precisely. Is it possible to get F of A inside B4 which satisfies the following? First is, of course, the embedding is proper. That is, the boundary goes to boundary. So boundary of the annulus goes to boundary. And the second, which is the most important, is that given phi, a diffeomorphism of A, phi equal to identity near boundary, given the diffeomorphism phi, of this annulus, which is identity near its boundary, there exists a family psi t of map from B4 to B4, psi of t equal to identity near delta B4. And this psi t conjugates and I0 equal to identity and okay. So phi is a self-diffeomorphism of A, and there is no reason for this to be isotopic to identity inside A. What I'm saying is that this diffeomorphism of A, which is identity on the boundary, appears as a when you embed A annulus A inside B4, this diffeomorphism appears at the time as a time one. So you look at the family psi t of diffeomorphism of this, and at time one, if you restrict this time one self diffeomorphism to which is isotopic to identity to your surface, then it induces the given field. Okay.
So this will be for any phi.
Yeah. So I will just tell that all this phi, we are only interested in diffeomorphism up to isotopy. So what you need to do only is for what is called as dentist diffeomorphism. So you can check that sufficient to produce an embedding which induces the following diffeomorphism. So you take A is equal to t comma theta going to so this is a kind of self diffeomorphism of 0 1 cross of the annulus, which is identity on the boundary, and this kind of geometrically does the following. You take an annulus, and if I look at this curve, and after applying the diffeomorphism, it kind of changes to this curve. So if you can do for this particular diffeomorphism, you can do for every diffeomorphism, because the mapping class group is generated by this for in this case. Okay. And this is actually given to us by nature. I mean, it is there. You know, you don't have to do anything. This kind of embedding is there everywhere. And let's just check that. So I said that so in order to get this embedding, you just do the following. So consider this model. So consider map f of z w equals z w, and consider f inverse of, say, epsilon. Okay. So if you look at this map and look at this particular map and just look at any complex number, I have just taken this epsilon, but as real, but you take any complex number and if you look at this inverse image, it is a, you can check that it is an embedded annulus inside C2. And if I look at this circle, so if you consider if I take this circle, so if I take this, okay, so if I take this circle, then you can see that if you follow this circle, you produce an isotopy of this 4 ball, which kind of comes back and induces precisely that map. You can just write down the coordinates and check parameter wise. So just this is the same model that we had in Lipschitz pencil, that map is F. So you have map from B4 to disk, and you look at a small circle inside disk, and you look at in the complement of 0, it is a fiber bundle, and you look at the what happens to the monodromy, you will see that you can actually produce one parameter family of diffeomorphism B, which induces then twist on this particular embedded annulus. Okay, and so this is just from the model that you have this property. Okay, I'm slightly cheating because you have to kind of make it agree with, but it's okay. So this, so you can use this model to actually solve that problem. And in fact, luckily, you can see that if you produce embedding in this way, then if you had already think symplectic, then this model is very well behaved with respect to symplectic structures, meaning this monodromy that you get is also a symplectomorphism. And so if you had a symplectic fiber bundle and you had to embed this annulus symplectically, then the inverse image of this also already is embedded symplectic. And now you kind of so now in order to get, so once you have this, it is kind of easy to embed every fiber bundle over wedge of circle or a circle. And that is because, so if you take sigma any surface, then the mapping class group I will draw a figure and explain. And if you take a surface of some genus G, then I can kind of on this draw some curves. And if I take its tubular neighborhood, these are all annulus. These are all different annuli. And you can show that if I perform then twist on, so any element, any diffeomorphism you take of this surface, then up to isotopy, it just appears as a product of then twist along this annuli. So it means there is a set of generated.
The theorem of first proved by Berlin, right? John Berlin.
I don't know.
Nielsen.
Nielsen, not before.
Not then.
I think.
Then is what I read a paper of Licorice where he attributes it to then, but
Okay, fine.
yeah. But these are, I mean, these are like, you can come up with a generator which are extremely good ones. So these are like original paper produces then twist along much more generators, but then you can kind of cut down the numbers and look for some simple kind. And so what we do is we look at neighborhoods of, we produce embeddings of surfaces inside 4 manifold such that this annulus, so surface, so there are balls inside the target manifold such that the intersection with this surface is precisely annulus that looks like xy equal to epsilon, zw equal to epsilon. And so then if you can produce such an embedding of surface such that its intersection with balls is just zw equal to epsilon, then you can produce a then twist on these guys. And so therefore this way you can produce embedding of any fiber bundle over a surface. And this kind of technique solves the second problem of extension over the singularity also automatically, because the model that we use to produce this Delquist is taken out of the singularity model. And so once you produce this embedding where this intersection of this annulus with your 4 ball is what is called as half annulus which looks like ZW equal to epsilon. It is automatic that you can extend in the interior where the 4 manifold, where the fiber bundle structure was not there, but there was a singularity. No, there's a natural extension. And so you combine, so that extension in local coordinate is given like this. You take, once you produce embedding of fiber bundle, you just need to embed the singularity, and that you embed by sending Z1, Z2 to Z1, Z2, Z1 into Z2. Where on the right hand side, I have a trivial fibration which goes ZW, Z1, Z2, Z3 to Z3. And you take this kind of diagonal embedding, Z1, Z2 going to Z1, Z2 into Z1, Z2, and you can check that all that we have produced matches with this embedding, and so there is an extension in the parts where fiber bundle structure is not different. And this kind of produces embedding of all 4 manifold that admit Lefschetz fibration. And in the contact case, again it was a bundle over S1, and it's a boundary went to boundary. So you look at, as I told you, that this open book decomposition has a property that near the binding, it just looks like some sort of X r theta going to theta. And since the embedding was proper, once you feel this, since the boundary goes to boundary, automatically the open book induces the open book here. So using that, you can produce embedding of 3 manifolds inside 5 manifolds. Okay. And maybe I have a minute or so. So maybe I can, this embedding, roughly speaking, is produced in the following simple way. It's not, I'll do some cheating because I cannot give all the details, but I want to convince that there is such an embedding. So you take CP1 cross CP1, just nothing but S2 cross S2, and you take, you want to produce an embedding of genus G surface that has that property. So you take 2 points and so these are like 2, I would call it as horizontal CP1s and n+1 vertical CP1s in this, because you can take this as x coordinate, y coordinate. So you take x into y1, y2, and here x1, x2, xn plus 1 and the whole y. So you have like 2 horizontal and vertical CP1. And notice that one CP1 cross P1, and so intersection of CP1 locally just looks like 2 complex plane intersecting at the origin, C cross 0 and 0 cross C. And again, so with this part corresponding to one CP1 and another part corresponding to another CP1. And we can again use our standard trick that replace Z1. So this is like, in this model's intersection looks like ZW equal to 0, because if you take the polynomial Z into W, Z, an inverse image of 0 is C cross 0 and 0 cross C. And so this locally looks like this, and you again resolve by the same trick. You replace this by Z1 Z into W equal to epsilon. So by doing this, you actually precisely produce an embedding where you have tubular neighborhood of annuli, which exactly looks like xy equal to epsilon. And so therefore we can produce any fiber bundle inside and then extend by that local formula. This way you get the embeddings. Yeah, I know.
You have a topological setting, you also have a theorem that any for manifold embeds in a CP.
Yeah, so there I have to kind of take local model of one-fold singularity into account. So there what we do is we think of this Lefschetz singularity as an attachment of two handle. But you can simplify everything and assume that you have a fiber bundle structure, so you have a map from 4 manifold to CP1, so that over one, so you can decompose the CP1 into union of two disks. Over this disk is honest Lefschetz vibration. But when you come from this disk to this disk, a round two handle is attached along the boundary. And so we kind of work out the exact local model of how the round two handle is attached and extend the embedding on the other part.
But this part not somehow work with in symplectic context.
Yeah, because this round one handle attachment has no nice symplectic model. Yeah. I mean, there is no one-fold singularity which is somehow compatible with symplectic structure. If one can come up, then one can think of it. But that part is not compatible with symplectic. Yeah.
Oh, it's the difference between the map between fibrations and what you reduced it to. Is that just the fact that the psi1 need not be the identity from B4 to B4? I mean, psi1, I mean, you reduce this map between fibrations to something of extent of like.
I'm just saying that, if you look at the diffeomorphism of a manifold, then something sudden happens, correct? It's not like a continuous family.
Right.
When you go into one higher dimension, you can actually see the film and so that it induces given diffeomorphism.
Sure. But this psi t is not something which is S1, right? Like going from psi 0 to psi 1 will not bring you back.
No, psi1 is not
It's not the identity.
Not
Okay.
it's
So
isotopic.
that's the difference between having the map between the fibrations and having this. No?
I don't understand.
Oh, when you have a map between the fibrations like this.
No, I mean if you have a family of embeddings, if you have an embedding and you have a family of isotopies that changes this embedding to something else, you can just close your eye and just see the film.
Yes.
Just put the film inside S1 part and that's the embedding.
Right. But here it's not an S1, right?
No, I don't understand. On CP1, cross CP1, there is a family of self-diffeomorphism that induces a particular diffeomorphism. And now we want to embed a mapping, a fiber bundle with a base S1 determined by that diffeomorphism into S1 cross CP1 cross CP1. And then you just close your eyes and put the fill S1 and you are done. Because you don't have to do anything. At every time T, you have an embedding, and at time 1, it comes back to itself with a different identification. That's all.
Sure. Okay.
That's all. So it in fact in S1 cross CP1 you have embedded.
Thanks.
Well, there don't seem to be any more questions. Thanks.